Have you ever wondered how you can feel the warmth of a bonfire even when you're standing far away? Or how we know the temperature of a star that's light years from Earth? Well, the answer to both is thermal radiation, and it is way cooler than you might think. Let's get into it.
All right, first things first. What makes radiation so special? I mean, we've got other ways to transfer heat, right? But radiation has a secret weapon.
Think about this for a second. The space between us and the sun is, well, it's space. It's a vacuum. There's nothing there to carry the heat. So how in the world does all that warmth make it across 93 million miles of pure emptiness to get to us?
Well, the usual methods of heat transfer, conduction and convection, are totally useless here. They need stuff to move through, molecules to bump into each other. But radiation? It doesn't need anything. It's pure energy, just zipping through the void in the form of electromagnetic waves.
And when I say zipping, I mean it. This is the fastest way heat can travel, period. It moves at the speed of light. That incredible 93 million mile journey from the sun, it takes that energy just a little over 8 minutes to get here. Wow. Okay, now here's where things get a little weird, but also really cool. This radiation thing, it isn't just for stars and fires. It's a fundamental rule of physics that applies to absolutely everything. Yes, that includes you. There's this principle called Prevost theory, and it's pretty simple. If an object has any heat at all, I mean anything above absolute zero, the coldest possible temperature in the universe, it's radiating energy. Right now, the mug on your desk, your chair, the walls of the room, they are all glowing with thermal radiation. You just can't see it. But get this, it's a two-way street. So while your hot coffee is radiating energy out to the cooler air in the room, the air is also radiating a little bit of energy back to the cup. The coffee cools down because the net flow of energy is from hot to cold. The coffee is just putting out way, way more energy than it's getting back. So you've got all this energy flying around. When it finally hits a surface, what happens next? Does it bounce off, go straight through, or does it get soaked up? Well, the answer is, it depends. Any given surface does a little bit of each. Some of the incoming energy gets reflected, kind of like a mirror. Some of it might be transmitted, passing right through like light through glass. And the rest gets absorbed. It's soaked up by the material, which makes its own internal energy go up. In other words, it gets warmer. And here's the key. Energy can't just be created or destroyed. So the amount that's absorbed, plus the amount reflected, plus the amount transmitted, has to add up to 100% of what hit the surface in the first place. It all has to go somewhere. Now, to make studying this easier, scientists came up with some perfect idealized models. You've got a white body that reflects everything, a transparent body that transmits everything. But the superstar, the one we really need to understand, is the black body. A black body is a theoretical object that is a perfect absorber. It soaks up every single bit of radiation that hits it. Nothing gets reflected or transmitted. Okay, so we've covered how things soak up energy, but what about how they give it off? How do they radiate it away? It turns out this is governed by one of the most powerful and honestly elegant laws in all of physics. First, we just need a way to talk about this. Scientists call it emissive power. It's basically a measure of how much energy is being radiated from every square meter of an object's surface, every single second. Think of it as the intensity of that invisible thermal glow. And that intensity is ruled by something called the Stefan-Boltzmann law. All it says is that the emissive power is directly proportional to the object's absolute temperature raised to the fourth power. Now, that T to the fourth, that is a huge deal. It means if you double an object's temperature, you don't double its radiation, you increase it by 16 times. It's an incredibly powerful relationship. And this is where our friend the black body comes back in. It turns out that a perfect absorber is also a perfect emitter. A black body radiates the absolute maximum amount of energy possible for any given temperature. Real-world objects, which we can call gray bodies, are always a little less efficient. They only radiate a fraction of what a perfect black body would. All right, this is it. This is where we connect all of this physics to something you can actually see with your own two eyes, the color of something when it gets hot. I mean, you've seen this, right? A blacksmith heats up a piece of iron. At first, nothing happens. Then it starts to glow a faint, dull red. Then it gets brighter, turning orange, then yellow. And if it gets hot enough, it can even become a brilliant white. So
Why the color change?
Well, the answer has a fancy name, Wien's displacement law. But the idea behind it is actually pretty straightforward. It just says that as something gets hotter, the main or peak wavelength of radiation it emits gets shorter and shorter, shifting towards higher energy light.
So that piece of iron at room temperature, its peak radiation is way out in the long wavelength infrared. We can't see it. But as you heat it up, that peak shifts. Eventually, it moves into the visible spectrum, starting with red light, which has the longest visible wavelength. Get it even hotter, and the peak keeps moving through orange, yellow, and white. That color is a direct fingerprint of its temperature.
So let's just zoom out for a second and appreciate how cool this is. We're about to connect the burner on your electric stove to the farthest reaches of the universe. So let's boil it all down. What are the big things to remember? 1. Everything with any heat is glowing with radiation. 2. The amount of that radiation goes up like a rocket ship as it gets hotter. Remember, T to the 4th. And 3. The color of that glow is basically a thermometer.
And this, for me, is the most mind-blowing part. These aren't just some rules for things in a lab. The very same physical laws that explain why a piece of metal glows red are what allow astronomers to look at the light from a distant star and tell you exactly how hot its surface is. It's truly universal.
So, I'll leave you with this final puzzle. You look up at the night sky, and you see a dim, reddish star and a brilliant, piercing blue star. Based on everything we just talked about, which one is hotter? Think about it. The answer is literally shining right there in the darkness. Thanks for tuning in.